Unit 2 is on asymptotes. Just put it on the desk right now. Asymptotes, continuity, the intermediate value theorem, average rate of change, and we will introduce derivatives. Four days of lessons, one review day, one test day. Test is 2 Wednesdays from today, or 2 Thursdays from today. Day 1 will be asymptotes, that's what we're doing today. Day 2 will be continuity and the intermediate value theorem. Day 3 and day 4 will be average rate of change and introduction to derivatives, kind of combined. All right, asymptotes. Asymptote is a line such that the distance between a curve and a line approaches 0 as they tend to infinity. We will worry about vertical and horizontal asymptotes in this class. We do not have to worry about diagonal asymptotes. We can see in this picture of this graph, we have a vertical asymptote here because my graph is getting closer to this value, this vertical line. And here we have a horizontal asymptote as we're going towards negative infinity on our x-axis. My function is approaching that value. Now, you could probably say that there's a diagonal asymptote here where this function would trend towards some line, that would have a slope that we could find, but we don't have to worry about that. You worried about that in past years, but not this year. Okay, so we can say this vertical asymptote is at this location. It would be an x location. Let's say it's A. The equation for it would be a vertical line or an x equals equation. Simple. As we are getting close to A from the left, we can see my function is trending down towards really, really big negative values. If I get close to A on the right, you can see my function is trending up to really big positive values. Horizontal asymptotes. In this situation, we have this value at, say, B. This line is a horizontal line, so the equation would be a y equals b equation. And as my x values go towards negative infinity, these function values are trending towards b. Yeah, when do vertical and horizontal asymptotes occur? Using calculus notation or limit notation, a vertical asymptote occurs when the limits as x approaches some value from the right or the left of a function equals positive or negative infinity. Vertical asymptotes occur when limits equal infinity, positive or negative. Now, I can't really equal infinity, but we'll talk about that. So if you see here, I could rewrite this instead of x is just equal to a. I could talk about the limits as x approaches a from the left of my function. And if I look from the left of a, what is my function doing? Trending towards where? Mr. Swisher. So to the left of a, negative infinity. And the limits as x approaches a from the right of the function, I see I am to the right of a, my function is trending up to positive infinity. In terms of equations, It's when we can't simplify a denominator. Take like 1 over x minus 2. Or if I wanted to find the limit as x approaches 2 or something like that. You would try to plug in 2 and you'd get 1 over 0, undefined value. But then you would try to simplify it algebraically. This is what we did last unit. You cannot simplify this equation so that we get rid of that pesky x minus 2. So since we can't simplify it, this will always be an undefined value, and it's the location of my vertical asymptote. If I have something like negative 2 over x squared minus 9. Sure, I can factor x squared minus 9 to be x plus 3x minus 3. That doesn't really help me simplify this thing. It just shows me that I can definitely not plug in 3 and negative 3, telling me that this equation has a vertical asymptote at x equals negative 3 and 3, because I can't plug in those values. Okay. Let's talk about horizontal asymptotes. Horizontal asymptotes occur when we analyze a limit as x approaches infinity. Positive or negative. So if the limit as x approaches positive or negative infinity of a function equals some value, let's just say L, the value, we will have a horizontal limit at L. Not horizontal limit, horizontal asymptote. So back up to this graphical example, I found the limits, and now we can put infinity, excuse me, thank you, down here. The limit as x approaches, I can put negative infinity down here. What I would be thinking is, okay, my inputs, my x values, they're going to be getting more and more negative. Are my function values trending towards a certain value? In this case, yes, it's trending towards b. However, I looked at the limit as x approaches positive infinity of this function. The way I would think about that is I'd be approaching positive infinity on my x-axis, all the way over here, and then some. What is my function doing? Well, my function is growing. It is not approaching some value. So you can say this limit either does not exist or it equals positive infinity because we're growing. Horizontal asymptotes. Now, we're going to first focus on vertical asymptotes. And here's a quick example. F of x is equal to negative 2 over x minus 3. I know I have a vertical asymptote where 3. Thanks, Ms. Fallon. It's easy. You can just look and say, can't plug in 3. If I plug in 3, we'd have an undefined value. That's the easy stuff. I mean, I could plug on a graph that I want to sketch. I could go ahead and place this dotted line here and say, there's my vertical asymptote. Great. But the more difficult thing is figuring out how my function is trending near that vertical asymptote. Is my function going to be going up like this from the left of it, or will it be going down from the left of it? Same from the right. Will we be going up as we come to the right, from the right of this value? Or are we going down? Okay, now if we had a calculator, it'd be a piece of cake, and we could just graph it and see it, of course. If we had like a simple calculator, we could plug in values, and we can analyze this numerically. This will be a good exercise just to kind of prove a certain point. So I can numerically find the limits as x approaches 3 from the left. I plug in different x values. X values like, I don't know, I could start at 2. That's to the left of 3. I can do 2.9. I can do 2.99. Maybe go even 2.999. What I'd get, I'd have negative 2 over 2 minus 3 is negative 1. That's positive 2. I'd get negative 2 over 2.9 minus 3 is negative 0.1. This is 20. I'd get negative 2 over 2.99 minus 3 is negative 0.01. That turns into 200. And then one more 9 added would be one more 0 added, both in the denominator and in my resultant value. So this is saying that as I'm approaching 3 from the left, my function is growing. And what also it's saying is that if I have a constant value here in the numerator, negative 2, negative 2, negative 2, negative 2, and I divide that constant value by an ever decreasing or smaller value, something getting closer and closer to 0, my result is a bigger and bigger value. And we could do the same thing for positive 3, and we could find out that it's trending to negative infinity. But this is kind of the idea we want to kind of understand right now. Is that if I have a value divided by an ever decreasing value, a smaller value getting closer to 0, my result is something that gets bigger and bigger and bigger. Or if I divide anything by something infinitely small, I'm going to get something infinitely big. Now, what do I think I mean by infinitely small, Mr. Thomas? Do you think I mean like a really big negative number, like negative 1,000? Is that like small? Or do I mean something else? What do you think? What's infinitely small mean? A big negative number or something else? What's the something else? What would be something infinitely small? Good. Making sure you're paying attention there, Mr. Thomas. Yeah, something really, really close to 0. Okay? Not negative. And we'll have notation to use for these infinitely small values. And you're already familiar with the notation. And you're already familiar with these values. 0 with a negative sign in the exponent. What does that stand for, Mr. Sexton? Yeah, 0 from the left. What would be an example of a number approaching 0 from the left, Mr. Barron? Yep, just give me an example. Just give me one.
3.
Yeah, but closer. I want something like really, really close to 0, but from the left. Yeah.
0.001.
Yep, but since it's from the left, it's got to be negative. Right? Think about a number line. If I look at a number line and I have 0, 0 from the left would be right here. That'd be a negative value. So, of course, I will go 0 with a plus sign in. That would be approaching 0 from the right. And that would be a positive, really small value, 0.0001. Okay? So why am I using this? Well, what we're going to be doing is instead of using negative 0.0001, I'm going to say, what's this? And you are going to tell me, it's that. Let's talk about that. Don't worry about it. It might be confusing. Let's think about just these situations, okay? Think about k being some positive value, not a value, just a number. And we'll talk about our denominator being these very infinitely small values. So k is a positive number. You could say k is like 5. If I take a number 5 and I divide it by something infinitely small, but to the left of 0, so it's infinitely small and negative, something like this, what do I get, Mr. Fig? Yeah, something really big and negative. Just a value divided by something infinitely small will be something infinitely big, but since it's a positive divided by a negative, it'll be a negative. We'll say this is approaching negative infinity. So if I have positive value like 5 and I divide it by something infinitely small that's positive, this would be something infinitely big and positive. Think about like 5 divided by 0.0000000001. That's infinitely small number going into a value. We can go into that value almost infinitely many times. Okay, and this is what we kind of saw in this numerical example. As I got smaller and smaller, this value gets bigger and bigger and bigger. So what would be the last two, Mr. Packer?
The positive infinity and negative infinity.
Exactly. As long as we understand the concept, all we have to worry about is the signs. This would be a negative divided by a negative, which is a positive. This would be a negative divided by a positive, which would be a negative. Piece of cake, right? Cool. Well, we're going to use all these tools to help us not really worry about the location of a vertical asymptote. The location is the easy part, but it's how our function is going to be trending around this vertical asymptote. Will we be going up from the right? Will we be going down from the right? Are we going to go up to positive infinity or negative infinity? Who knows? Okay. So here's our first function, negative 1 over x minus x plus 1. I know just by looking at this, it says a vertical asymptote at x equals negative 1. But I don't really care about that. I care more about whether my function is going up or down in relation to this vertical asymptote from the left and from the right. And here's how I'm going to do this. If I were doing this like a regular limit problem, my first attempt would be to plug in negative 1, right? And then if I get an undefined value, I'd try to simplify. Well, we should be able to see this and know that I can't simplify. So I'm actually going to go ahead and plug it in like I would normally do on a problem that was easy. Only when I plug it in, I will include the from the left. Now, in my mind, I will be thinking, okay, I got negative 1 over a value that is to the left of negative 1. I'm going to be thinking maybe about a number line here. And I'll think, okay, this is 0, this is negative 1. A value coming from the left of negative 1, that's like right here. That's like negative 0.001. That's what I'll be thinking in my mind. But then I'll go ahead and say, okay, I got negative 1. This value here is going to be essentially 0. It's going to be approaching 0. The key is it going to be approaching 0 from the left or from the right? Will it be an infinitely small negative value or an infinitely small positive value? This here is a little bit bigger in terms of a negative number than this. If I add these two numbers together, I get a negative number. And then, knowing that we have a constant divided by something infinitely small tells me that we are growing to be something infinitely big. And since we have a negative divided by a negative, it's a positive. Okay, you guys do the same procedure for the second one. And then check your answer with a neighbor. And talk through it with a neighbor. Write it on your paper. Don't do it all in your head. I'm sure you can, but it's going to help you if you wrote it down. Check with your neighbors. Good. Check with your neighbors. Make sure you get it right. Everybody. Mr. Wimbush, check with Miss Vanderstraten, check with Miss Slade. Mr. Sexton, you got it? Think so? Did you check with a neighbor? Go check with a neighbor. Check with Mr. Ortle. Mr. Mogadam, check with Mr. Ortle behind you. All right, I plug in the value. Now, you might not be here yet where you need to do this in your mind. You might have to write down this step. And that's okay if you write down the step. Because you got to think about a number to the right of -1. To the right of -1 is over here. That's like -0.999 repeated. So this is -0.9999. Include as many nines as you want. It's there just to show you that this is a little less negative and this is positive. When I combine them, it will be a value approaching 0, but it will be a positive value. So infinitely small positive value, approaching 0 from the right. This, we should know, something divided by something infinitely small is something infinitely big, and in this situation it's negative because we have a negative divided by a positive. Cool? Now, Mr. Sexton, you're taking your test after school today. What would this limit be in general? So, I know the left-hand limit, I know the right-hand limit.
It would be undefined, right?
Yeah, it would be does not exist, and why? Why?
You can't divide anything by 0, and then nowadays the denominator equals 0, if you plug it in, and you can't simplify it.
Sure. What I was looking for is the left-hand limit is not the same as the right-hand limit.
Oh, also that.
Okay, good, good. So you know it's an asymptote, boom, you know that there's no limit. That's perfect. And it's the same idea. Okay? All right. Let's do this one. I'll show you one, you'll do one, and then we'll talk about the limit in general, and then we'll do a couple more practice problems, and then we'll keep going. So, limit as x approaches 4 from the left of -5 over x minus 4 squared. All right. I got -5 over, I know we have an asymptote at 4. That's apparent. If I plug in 4, I get 0 in the denominator. So I'm thinking -5 over a value to the left of 4 minus 4 squared. In my mind, I'm thinking 3.999. So you're looking at a number line, and this is 4 to the left of 4 right here. That'd be like 3.9 repeated. Well, that number minus 4 is going to be close to 0, and it's going to be negative. If you can't see that, you do the step in the middle, and you say, okay, 3.999 minus 4. Okay, this is less than this, subtracting a bigger number. This will be something that has to be negative. But now I have to square this value. If I square something infinitely small and negative, it will still be infinitely small, but it will turn into a positive. Divide something by something infinitely small, something infinitely big, but it will be negative in this case. Okay, do the other one. Check your answer with a neighbor.
Take a number, like a next biggest whole number, like 1, 5, and you divide by 4, and figure out the positive or negative.
Sure. That works. I like to keep it close so that I know we're getting close to 0. But if you can keep that in your mind, that's fine. All right, what do we get, Mr. Giuffrida?
Negative infinity.
We also get negative infinity. It's good. Negative 5 over 4 plus minus 4. The process should be we should have negative 5 over 0 plus squared, which will be negative 5 over remaining 0 from the right, which will be negative. Okay. Now, Ms. Pallet, if the left limit is negative infinity and the right limit is negative infinity, what is the limit in general? Sure, we can now say this limit is actually equal to negative infinity.
But they never actually approach that. So it can also be different.
Or it could be does not exist. Exactly right. You beat me to it, Mr. Barron. You beat me to it. Now, so what you're going to say is like, well, can we just put does not exist everywhere? Because if this doesn't exist, well, this is negative infinity. That's more of a concept rather than a value. We could say does not exist for all these, right? Yes. However, there will be questions where they won't give you does not exist as an answer choice. So you'd have to be able to figure out that this limit is negative infinity. Okay, that's how they get you. All right, I'll do another one. This is a good one to do. So the limit as x approaches 4 from the left of x minus 5 over x minus 4. So if I were to do this like the last couple problems, I'd go 4 from the left minus 5 over 4 from the left minus 4. Let's work with the denominator. I'm talking about 3.99 minus 4. It's just like the last problem we did. This will be 0, but a negative, infinitely small number. Now, 4 from the left minus 5. 4 minus 5 is negative 1, right? But is it negative 1 from the right or from the left, and does it matter? Right or left, Mr. Swisher? 3.9 minus 5. Is that going to be more negative? Good. It would be from the left. Now the question is, does it matter what goes here? Who says no and who can explain why? Go for it, Mr. Swisher.
It does not matter because they're both negative.
Well, what if this was a plus? Why does that still not matter? That's exactly right. It doesn't matter if it's from the right or from the left of -1, because from the right and from the left of -1 are still negative values. So I don't care that this is from the left of -1. Don't care. It's still a negative value, and it's still a value. It's a value. Here, from the left and right of 0, that's when we're talking about changing from negatives to positives. So this is still a value divided by some infinitely small value will be something infinitely big. And since it's a negative divided by a negative, it's going to be positive. Okay? Same idea, do this one. Check with a neighbor. That's from the right. That's a plus. -3 from the right. Check with a neighbor. Check, double check, turn behind you, ask the person behind you, turn to the left, check with the person to the left of you. Miss Vanderstraaten, we look confused. Do we got it? Consult the neighbor. That's important. So you get negative infinity. Okay? This one's really similar. We'll skip it. I want you guys to try this guy. Think about that thought process and go for it. And then talk through it with the neighbor. Number lines sometimes help with from the left and from the right.
I we should have chosen like an 8 sideways with everybody works and all trying to like length and off.
Yep. If you understand how you got that, then you're perfect. All right. This is the trick to this guy. -2 from the left squared. Well, yes, the -2 will be squared and it'll become a +4. But will be +4 from the right or from the left. I start as -2 from the left. Does that mean it's going to be +4 from the left as well? Definitely not. And the reason is because what are you squaring? You're squaring -2.0001. Okay? If I square that, I'm multiplying that by itself. That would be a number bigger than 4 because it's a negative number, a larger negative number. And you kind of plug into your calculator -2.0001 square and you get a number bigger than 4. So this turns into 4 from the right. -4. Well, that's going to be 0 from the right. 5 over 0 from the right is something very, very big and positive. Okay, do the next one. Check with the neighbor. Mr. Thomas, I'm going to call on you repeatedly, forever, until you put the calculator away, because you're cheating. That's how it works. Yes. You can sleep, you can use your calculator, you can use your phone, all of those things will get you called on repeatedly. All right, Mr. Bonner, did you get it? What did you get? Good. This is -2 times 3 from the left. That ends up being -6, but I don't care if it's from the left or from the right. 3 from the left. 3 from the left squared. 3 from the left squared. This is a number that is less than 3. So when you square it, it will be less than 9. That is fact. So when I take this 9 and subtract this number just a little bit less than 9, that's a number that will be positive and close to 0, making this negative infinity. Okay, so it's not about switching signs. It's just thinking about the numbers that you have and what happens to them. That's important to remember. A lot of people are going to want to use tricks to say, oh, I have a negative here, so this means it's a negative here. Sure, maybe it works in some situations, but not all situations. Instead, think about numbers, don't use tricks. All right, let's do some even funner ones. That's a word? Yeah. Let's do these one-sided limits involving trig functions. So we have the limit as x approaches pi over 2 from the left of 1 over cosine of x. If I were to do this problem just like the last one, I would try to do 1 over cosine of pi over 2 from the left. I know the cosine of pi over 2 is 0, but the question is, what goes here? Got to be from the left, right? This is a minus. This has got to be a minus. Let's see. All right. We're going to go with it. Let's see. This is going to be a unit circle that will really help you. I would advise you to draw a unit circle on your paper somewhere. It is very helpful when we're dealing with one-sided limits involving trig. Also, you might want to include a number line, just so you understand coming from the right and coming from the left when we have this two-dimensional thing. So let's think about it. I got 0, I got pi over 2, this is a number line, pi, 3 pi over 2, 2 pi. Pi over 2 from the left. That is starting at 0, traveling towards pi over 2. We have a value that is less than pi over 2. In my unit circle, if this is 0 and this is pi over 2, pi, 3 pi over 2 on the bottom, where would pi over 2 from the left be? Would it be over here in the first quadrant or over here in the second quadrant? First quadrant. We're traveling from 0 to pi over 2. These are radian values less than pi over 2. This is pi over 2 from the left. So that's the first step. We're going to fill in the rest of that unit circle in a second. So cosine of pi over 2 is 0. However, if I'm talking about pi over 2 from the left, I'm talking about cosine values in this first quadrant. Okay. Well, if we use this ASTC, this is going to help us as well. The all students take calculus. This tells us which trig functions are positive in which quadrants. Well, the cosine values where we're to the left of pi over 2 are positive in the first quadrant. So yes, we're approaching 0, but since cosine is positive in the first quadrant, we'll be approaching 0 from the right, or we'd be having a positive infinitely small value. Meaning this would be something infinitely big and positive as well. Now, I'm going to give you guys this one to figure out. And I'm not going to fill in the unit circle. I'm going to make you figure out where pi from the right is yourself. Help using a number line. I will draw an arrow. That's all I will do. That's pi from the right. All right, try it. Check with a neighbor. Not everybody checked. I want everybody to check. Try to walk through the problem with a neighbor if you can't get it or if you're really unsure. Right. That's important.
It's coming to everybody would do that way. So. 1 over 2.
Doing math without numbers.
I agree.
All right, Mr. Wimbush, you get it? Negative infinity is correct. This right here is pi from the left. Right, sorry, from the right. Coming from 3 pi over 2 to pi, coming from 3 pi over 2 to pi, this is pi from the right. So I know that the sign of pi is 0, but it will be negative values because the sign in the third quadrant is negative, so it would be approaching 0 from the left, making this negative infinity. Now, a good idea just to have as a helpful kind of chart for homework is to fill this out so that you know which ones are from the right and which ones are from the left. And it's not that bad if you think about if you're going around the circle. If I'm going from smaller values to bigger values, I'm going in the counterclockwise direction. Okay? So if I'm going from 0 to pi over 2 to pi to 3 pi over 2, I'm coming from the left. So counterclockwise is the same as coming from the left. So if I'm going to pi, this would be from pi over 2 to pi, this would be pi from the left. 3 pi over 2, this on the left would be 3 pi over 2 from the left. This could be considered 0 or 2 pi, both from the left. Okay, so coming from 0, going to greater values, that's going from left to right, coming from the left, that's the same as counterclockwise. Clockwise, we're coming from bigger values to smaller values, that is coming from the right. So from 2 pi to 3 pi over 2, this is 3 pi over 2 to the right, from the right, pi from the right, pi over 2 from the right, 0 from the right, or 2 pi from the right. Okay? So that might help you. Do this one. That's the limit as x approaches 3 pi over 2 from the left. Get it? Check your answers with a neighbor after you get it. All right, Ms. Thorne, you get it? What'd you get? Positive infinity is correct. 3 pi over 2 from the left is right here. Cosine is negative there. Cosine of 3 pi over 2 is 0, but it would be 0 from the left. Negative divided by a negative, positive. Okay? Quick, without doing anything on the paper, what's 1 over sine of x as x approaches 0 from the right? Think about it, think about it, think about it, think about it. Don't do anything on your paper, and don't even look at your paper. This one. Just don't look at your paper. Is it your free? Did you get it?
No.
No? All about where 1 from the right is. I mean 0 from the right. Where's 0 from the right? It's positive because 0 from the right is here. Coming from pi over 2, bigger values to smaller values, that is positive. This will be 0 plus, this will be positive. Okay? Tricky. One more, this one. This one you can do on your paper. You can do cosine over sine if you wish. I would probably prefer, that's how I would prefer to do this problem. Did you get it, Mr. Thomas? Okay. What do I have on the top and what do I have on the bottom? That's okay. Top is important too. So let's walk through it. Cosine of pi. Cosine's the horizontals. Over here, -1, good. Now, is pi from the left in the second or the third quadrant? Second is correct. So, is sine positive or negative there? Good. So this is negative infinity. All right. Sweet. Those are vertical asymptotes. Let's do horizontal asymptotes. We're not done yet. We go bell to bell here. Fourth period B days. We always go bell to bell, Miss Carr. Get used to it. Here we go. All right. To find a horizontal asymptote, we need to evaluate the limits of the function as x approaches infinity. Here is a function. I would have to figure out the limit as x approaches positive infinity and the limit as x approaches negative infinity. The concept, if we had a calculator, would be to plug in bigger and bigger values for x. So maybe start at 1, but maybe go 10 to the 4th power, maybe 10 to the 20th power, maybe 10 to the 100th power. Those are what we're talking about. Huge numbers we'd be plugging in and seeing what our function would be doing as we plug in these huge, huge values. I'm not going to do that, but I'm just going to tell you, in this case, it trends to 2. And if I looked at negative infinity, I'd be talking about the same values, just negative. Huge, huge values. Not 1,000. 1,000 is small. Not 1,000,000. 1,000,000 is small. 1,000,000,000 is small. 1 followed by 100 zeros. That's starting to get there in terms of what we're thinking about in terms of big values. Okay? So this one would also be 2. I can't tell you why yet, but I will. Because there are going to be guidelines with these limits at infinity. Yeah, today. Now what's great is after we learn this, and we learn that we have an asymptote as 2, we can combine my horizontal asymptote with the vertical asymptotes I just learned about. Where does this function as vertical asymptotes? 4, -4. Because I can't plug those values in and I can't simplify. Now, without doing any work, can anybody tell me what the limit as x approaches 4 from the right is of this? So 4 from the right, that's 4.001. Square it, it's a number a little bit bigger than 16. Subtract 16 from that number a little bit bigger than 16. It's a number that's approaching 0 from the right. This will be positive. This is how we're going to be approaching from the right, this 4. Now from the left, 4 from the left, what is it going to be? Positive or negative infinity? 4 from the left. I square 3.9 repeated. I get a value a little bit less than 16. I subtract 16 from it. It's negative. And then, of course, this 4 squared will stay positive. We'd end up with something like this. And we can kind of do this now with our asymptote knowledge. And the reason why I went up to 0 is because you plug in 0, you get 0 over negative 16. So 0, 0 is a point. Okay? All right. Here are your guidelines for finding horizontal asymptotes. There are 3 guidelines. Okay. The most important thing to remember is your highest power term is going to be the most influential in determining your limit. And it's not necessarily in your function, but it's in your numerator and denominator.
I don't know. I feel like that 1,000 times tends to be a little more influential.
Yeah, but you got to think what you're doing with that 1,000 times x squared. What are you plugging in? What values are you plugging in? If I plugged in 1, what's going to be bigger? 2x cubed or 1,000x squared? 1,000x squared. Cool. What about if I plug in 1,000,000? And if I take 1,000,000 and I cube it, is that going to be bigger than 1,000?
Slightly.
Yeah. And as I plug in bigger and bigger and bigger and bigger values, if we look at this function, this 1,000x squared would end up being insignificant. I know it's such a big thing.
No, I understand that, but the 1,000x squared can be influential, like more influential.
At the beginning,
Depending on the number.
the 1,000x squared is definitely influential. This is a good point. But it is influential when we're talking about small values. When we're talking about infinity, it becomes like a decimal point. It becomes like adding 0.0 followed by 10 zeros, 1 to 1. If I add 0.010 times 1 to 1, it's still 1, right? That's what this is. This is like a 0.0 repeated with a 1 at the end compared to this when we're talking about this. Okay? So in the denominator, in the end, as I'm plugging in bigger and bigger values, this will grow significantly faster than this term and this term, making those things insignificant if we're talking about huge values.
The third term's not going to grow.
No, that third term will not grow. So you definitely know that's not going to be influential. Good. Now, if we think about it, we end up with this limit. 2 ways to do this. You can either just think about it theoretically, or you can do it a little bit algebraically. Theoretical, I'll do first. If I'm talking about limit as x approaches infinity of just this, because the other stuff really doesn't matter, because we're approaching infinity. This term will be growing faster. We're talking about growing faster. And this will be slower. Which means we will be getting bigger values and bigger values till in the relative sense, will have a huge value that will continue to grow at a huge rate over a tiny value that will be growing at a smaller rate. Even though it's, they're going to be similar to begin with. So as this huge value grows and we're dividing by a relative smaller and smaller value, what does that entire thing trend towards? Bigger, bigger numbers. That's how we can think about that theoretically. Algebraically, 2 L's. If, after getting rid of my insignificant stuff, I end up with this, I can cancel 2 x's in the top and in the bottom, giving me 2/10 x. X in the top, no x's in the bottom. As x approaches infinity, this entire thing will grow to be infinite. Right? Just makes sense. Be 2/10 times a big number. Okay, I just canceled 2 of these x's. You can make this 2/10 as, 1/5 if you really wanted to, and you could have done 1/5 times x. That's guideline number 1. Now, do whatever you want to do for this guy. I'm going to change it a little bit. Let's make this 4x cubed minus 2x over 1000x squared plus 50. This is the limit as x approaches negative infinity. Go figure that out. Check with a neighbor. Talk about it with a neighbor.
You switched it out.
I did switch it out on you. I put it in red just to make sure. It's red and slanty, you're right. And I know I didn't do it after. I did it right. I did it before. This is a negative infinity. Insignificant. This will grow faster than this. However, we're plugging in negative values. So this is going to grow faster and be a huge negative value. I plug in huge negative values in for this and I square it. It will be positive, but comparatively it'll be tiny, giving me negative infinity. If you do it algebraically, you'd have 4 over 1000 x, but you're plugging in negative infinity, so that's going to be a huge negative value. Guideline number 2. So we're talking about the degree of the numerator is greater than the degree in the denominator. We got positive or negative infinity. Second, the degree of the denominator is greater than the degree in your numerator. I don't want to say that. Okay. Here, negative 5x to the 4th plus 20 over 2x to the 5th. We'll do it both ways. A quick note, what happens when we take this positive value like 5 and I divide it by something infinitely big? So, something like that. You get something infinitely what, Miss Pallop? Small. Something infinitely small that is approaching 0. Very important concept. We talked about dividing things by infinitely small things and getting infinitely big things. If I take something and divide it by something infinitely big, it'll be infinitely small. Right, Mr. Thomas? Yes. Now, theoretically, if I want to do this, the 20 is inconsequential as I plug in bigger positive values. This becomes negative 5x to the 4th over 2x to the 5th. I plug in values. This would end up being a huge value compared to the smaller, tiny negative value. Something that will grow faster in the denominator relative to the numerator will approach 0. If I want to talk about this algebraically, it would be the limit as x approaches infinity of negative 5x to the 4th over 2x to the 5th. Cancel a bunch of x's, you get negative 5 over 2x. If I plug in a bigger value, I get negative 5 over infinity. That's 0.
You have to specify which side it approaches 0 on.
Good question. No, thankfully. I don't care about signs.
So, if the denominator is bigger than the numerator, that's 0. You really don't even have to work it out.
Nope. Sweet.
Those problems.
This is why we do in the second. What? All right. Third guideline. We're talking about numerator bigger than denominator. We got positive and negative infinity. We got about the denominator having a bigger degree than the numerator. We're talking about 0. So what if the degrees are the same? Best way to show this is the algebraic way. The 2x, the negative 5, will mean nothing compared to the x cubes. And I want to find the limits as x approaches infinity of just this. This simplifies to just be negative 4 over 1, which is just negative 4. If the degrees in my numerator and denominator are the same, you use your coefficients of your highest degree terms. Not done yet. What about, we're skipping a lot of problems here. This guy. We mean no. You just say no. Good. Mr. Barron, you're correct. I can get rid of the negative 2 and the 1 because those are insignificant. Turns into this. The square root of something squared is just what we start with. So, what has a higher power? The denominator or the numerator? They're the same. So, it's not 3/2, 3 over root 2. Because it's not 2, it's the square root of 2. You can split this to be root 2 root x squared. Now, I don't want you to go all the way down to root 2 times x, and I'll show you why. Look at this. Same deal. However, when I plug in negative infinity into my numerator, that would make it a negative value. When I plug in negative infinity into my denominator, I have to square that, which makes it positive, and it will remain positive. This is negative root 3 over root 2. or negative 3 over root 2. So when the degrees are the same, you still have to worry about the signs, especially with these square roots, and almost always just with these square roots. Okay? Use the highest degree, coefficients of the highest degree terms, careful with signs. Okay? Because think about the values. We have a negative infinity here. I plug it in here, that'd be negative. I plug it in here, it'd be positive. Negative over a positive is a negative. First one we already did. It's definitely positive. Not done yet, Mr. Bagger. Double bell. All right, good. All right. Limit as x approaches infinity of the sine of x. This does not exist. Sine goes up and down forever and ever and ever and ever. It'll never approach a value. So, what would this be? Nope. That's only when x approaches 0, guys. You know that. Sine x over x when x approaches 0 is 1. What is that limit as x approaches infinity? Think, Ms. Carr. Give me the answer. Think a little harder. I'm plugging in infinity in for this x, and I'm plugging in infinity for this x. Sine goes up and down, up and down, up and down. So sine will go up and down and up and down and up and down. The denominator will grow. What happens to the entire thing? Anybody?
0.
Thank you. It goes to 0. This will go up to 1 and down to negative 1. That's it. This will continue to grow. The entire thing will approach 0. There will be different problems like these as well. There is a video already online that I went through more problems. I would advise you, if you need help on these, to watch the video. This will go up and down. It won't grow at all. This will grow. The entire thing will approach 0. Think about the next one. I plug in negative infinity here. Sine will just continue to oscillate between 1 and negative 1. It will become insignificant compared to anything with a power, like 2x, which has the power to the first power. I plug in negative infinity multiplied 2. It's negative. So I have 1 over this huge value that's negative. It doesn't matter. We are approaching 0. Let's look at the next one. The limit as x approaches infinity of the cosine of 1 over x. I plug in a huge value, or like infinity, 1 over something huge. That'll be 0. This turns into just the cosine of 0, which is 1. Interesting. I think about this guy, the limit as x approaches infinity of x over sine of x squared. Well, sine of whatever value squared will just oscillate. It'll just go up and down, that's it. So it won't grow. It'll almost be stagnant compared to the growth of this. This will continue to trend towards infinity. This will oscillate between positive and negative, positive 1 and, actually this will always stay positive, no, but it will still oscillate between positive and negative 1. This would trend towards both positive and negative infinity. This almost would be too tough to describe. I would say it does not exist. Let's look at sine of x over x, so x over sine of x squared. Yeah, see, as I get further away from 0, my function will grow more and more, up and down. You can't even see it here, but it's growing so fast as we get further and further away that you can't even say that it's positive or negative infinity. It's just crazy oscillations and crazy growth from a huge positive value to a huge negative value. That's a crazy graph. So definitely does not exist. You'll typically deal with more of things like this or like, this, where signs oscillating, denominators growing, get 0. Finally, limits involving variable powers and then log x. So what grows faster? The question is x cubed or 3 to the x? This guy definitely grows faster. If we're talking about highest degree terms, this value will always trump whatever number we have here. And if we have 2 numbers to powers, this will grow faster, and that will dominate. So if you have a deal where you have the limit as x approaches infinity of 3 to the x over x to the 10th plus 3x squared, and this is 3x plus like 2, this will dominate. Everything else will be inconsequential. We'll have a huge value divided by a smaller value, making something huge. E to the x or log x? Well, log x confuses people. It's really not that tough. E to the x is definitely going to grow faster. Important to know what log x looks like. Log x definitely does grow. It's the inverse of e to the x. It's just e to the x flipped over. E to the x grows exponentially. Log x grows, but at a decreasing rate. Okay? So log x does not grow fast. And compared to anything like, if you compare log x with x squared will definitely grow faster than log x. So final question, which one of these will equal 0? This will grow faster than this. This dominates positive infinity. Let's look at this one. Even though this is x to the 99th, e to the x will go faster than x to the 99th, positive infinity. Here, log x, e to the x, e to the x goes faster than log x. This approaches 0. Hope this video helped. Hope this helps you on your homework. Come in with questions before or after school. But hopefully these rules, these guidelines, remembering the first one, degrees higher than the top than in the bottom, positive or negative infinity. Degrees higher in the bottom than in the top, we're approaching 0. Degrees are the same. Forgot to include this. The degrees are the same. Use the coefficients. All right, thanks.